We will begin a review for test 3 that will cover the topics listed here. In this first part, we're going to look at the neutron stars, pulsars, and black holes. Hopefully the equations that you see here is familiar from when we originally covered it. So the first topic, let's begin the first topic, neutron stars and black holes. And of course, here is a picture of a black hole. It's not a real picture, it's an artist's simulation of what a black hole would look like. It would lens the area around it, serving as a gravitational lens. When stars die, we find that they burn up all their nuclear fuel, and the heavier elements are at the center, like iron, then followed by lighter elements like silicon, carbon and oxygen, helium, and finally hydrogen at the top. But compact objects more massive than the Chandrasekhar limit, which is 1.4 times the mass of our sun, collapse even further. The pressure becomes so high that electrons and protons combine to form stable neutrons throughout the object. So these stars, which are red supergiants, as shown in the picture below, become the fuel for the next set. Hydrogen fuses to helium, helium fuses to carbon and carbon and oxygen fuse to neon, magnesium, and so on. Thus, as a red supergiant undergoes successive stages of nuclear burning, iron eventually forms in the core. As the iron gains mass, it eventually reaches this Chandrasekhar limit of roughly 1.4 solar masses. At its mass limit, the iron core collapses due to gravity. It collapses so small, it is only about 10 kilometers in diameter, liberating a tremendous amount of gravitational energy. Microscopically, the electrons and protons combine to form neutrons and neutrinos. The pressure support previously provided by most of the electrons disappears until the star is just a ball of neutrons, a neutron star. Although they have about 1 to 3 solar masses, they are so dense that very few, they are very small. This image shows a 1 solar mass neutron star about 10 kilometers in diameter compared to the island of Manhattan. This great density means that a piece of that neutron star, the size of a cube, has a mass of about 100 million tons. Neutron stars were theoretically predicted in the 1930s, but they weren't actually discovered until 1967, when Jocelyn Bell, a graduate student working with a group of English astronomers, discovered a periodic signal in the radio part of the spectrum coming from a distant galaxies. Briefly, astronomers considered this a signal possibly from an alien civilization. But as they looked at it a little closer, they found out that this was just a spinning neutron star.
Pulsars are spinning neutron stars that emit narrow beams of radiation in opposite directions. As the pulsar spins, the beams sweep across space. If the beam happens to point toward the Earth, we see a pulse of radiation each time the beam sweeps past the Earth.
So these objects called pulsars are just rotating neutron stars serving as beacons. Every time the beacon crosses our path, we see a pulse. How did this come about? Well, when the neutron star collapsed into this tiny, tiny ball, it sped up. Its spinning sped up because of conservation of angular momentum. The closer the mass is to the center, the faster it will spin. So collapsing new star's stellar core spins up to about a few milliseconds. Very strong magnetic fields are around this neutron star, which is why we see this period. We know it has to be small. No object can be rotating this fast because an object cannot change its brightness in an interval shorter than the time it takes for light to travel across it. So if pulses are no longer than about 0.001 seconds or 1 millisecond, then objects cannot be larger than 300 kilometers because light will travel that distance in that amount of time. This enables us to find the size of these objects. Just like white dwarfs, which have a Chandra-Scaler limit of 1.5 solar masses, there is also a mass limit for neutron stars. Neutron stars cannot exist with masses greater than 3 times the mass of our sun. We know of no mechanism that will actually halt the collapse of an object this large. Gravity will cause it to collapse to a single point, which we call a singularity, hence the name black hole. Let's look at a little more detail about the makings of a black hole. As a star collapses, its radius gets smaller. We have studied earlier that there is an escape velocity from any planet, or from any star for that matter. That escape velocity is given by this formula. So as a star collapses, as r, the radius of the star, gets smaller, this escape velocity gets bigger. But there is a limit to how big this escape velocity can be. And the limit is the speed limit of the universe, which is the speed of light, which we call c. So what is the smallest that r can become? Therefore, what is the biggest that the velocity v can be? If we solve that equation for v, letting v equal the speed of light, we get that the radius is equal to 2g times the mass of the star divided by the speed of light squared, which means that once the radius becomes this small, nothing can escape from this black hole, not even light. This radius is called the Schwarzschild radius, and at this distance from the black hole, nothing can be seen from the outside. So even though the mass may have shrunk to this tiny, tiny distance right at the bottom here, up to a radius r of the Schwarzschild radius, no information can get out from within a black hole, cannot get out. Nothing can escape, not even light. And this is called the event horizon.